Today we're going to start talking about counting combinations, now with repetitions allowed. What we did before was we talked about the number of combinations that we can have of length k from an n-letter alphabet, but no repetitions were allowed. When you don't allow repetitions and you have combinations of length k from an n-letter alphabet, the number of such things is called just n choose k. And we already showed that the value of n choose k can be written as n factorial over k factorial times n minus k factorial. Remember, just as a quick review, we can also write this as n times n minus 1 times n minus 2 all the way through n minus k plus 1 over k factorial, which is 1 times 2 times 3 up to k. So that's when repetitions are not allowed. But how many combinations can we have of length k from an n-letter alphabet? If you do allow repetitions, you can have several of any letter or multiple letters. Well, we give a name to that. We call that n choose k with a subscript r. And we read that as n choose k with repetitions. And we're going to be computing that. Actually, we'll be computing that in the next video lecture. In the rest of this video lecture, we're going to be computing the answer to a slightly different question, which will help us on our way to computing n choose k with repetitions. Now we're going to count combinations with repetitions, with no missing elements. How many combinations are there of length k from an n-letter alphabet if letters may be repeated but no letters are missing? And by that we mean each of the n letters in our alphabet appears somewhere, at least once, in our combination. The first thing I want to note is that if you have a k letter combination, or a combination of length k, and there are only n letters in the alphabet, and every letter has to appear once, then we must have k greater than or equal to n. That's certainly true. Every letter has to appear at least once, so the length of the combination better be at least k for that to happen. Of course, the length of the combination can be much bigger if there are lots and lots of repetitions. Here's an example. How many 14-digit combinations, I'd written that incorrectly at first, are there from the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, that's a 9-letter alphabet, if the combination must contain each digit at least once? One such, I should have written that differently, one such combination is given by this one here, 1, 1, 2, 3, 4, 5, 5, 5, 6, 6, 7, 8, 8, 9. I've written another possible combination here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 9, 9, 9, 9. These are each 14-digit combinations, and they use the digits 1 through 9, each one at least once. Now you'll notice that I wrote these combinations in numerical order. I started with a 1 and I put them in increasing order up to the 9s. Doesn't matter if I do this? Well, it's a combination. Order doesn't matter. I could have written the first one as 5, 5, 6, 5, 6, 7, 8, 9, 8, 1, 1, 2, 3, 4. They're the same combination. So just as a matter of practice, in order to do the computations that we're going to be talking about soon, I'm going to just choose to write the combination with the letters, which are the digits here, in numerical order. Our question now will be, how can I create such combinations, 14-digit combinations containing each digit at least once? How can I create them? And I want to answer that question in such a way that I can count the number of ways that I can create them. So if I choose to, and I'm allowed to choose this, write them in increasing numerical order, we know that I'll start writing here a 1, because there has to be a 1, and that will be the smallest digit. And somehow at the end here, there has to be a 9. And I have 14 spaces written here. You can check that. I hope that's right. I just counted them real quickly in my head. There are actually 14 spaces. So those have to be that way. It has to start with a 1 and end with a 9 if I happen to choose to put them in numerical order. But now I have lots of possibilities. I could have multiple 1s as I do in this first combination. So I could put more 1s here. I could jump immediately to a 2. When I put a 2, I could put 2 2s or 3 2s, and somewhere I have to jump to a 3. Somewhere I have to jump to a 4. And we keep going until at the end I have to get up to a 9. If I get a 9 earlier, I just have to use 9s all the way till the end. Here's a question. How many times do I have to jump, moving from 1 to 9? Well, the answer should be clear. I have to increase the number 8 times. I have to increase to a 2, increase to a 3, increase to a 4. I do that 8 times to get from a 1 all the way to a 9. And then I can ask myself, where do I make those jumps? One possibility is I put those 8 jumps here, 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 and here. Say here. Those are 8 places where I could make the jumps, and that would give me the string 1, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 9. That's different from these other combinations, but I get this new combination. Now, here's something to know about the places where we make the jump. The places have to be between these dashes. There always has to be at least one of each and every digit from 1 through 9 appearing, so that digit will appear between 2 successive jumps. If I choose 8 places to make jumps, I'm starting with a 1, ending with a 9, I'll use every digit at least once. My question then becomes, how many different ways can I place those 8 positions for the jumps? Well, that's not a difficult question. I'm going to put now 14 blank spaces again. One more over here. Here are my 14 blank spaces. Okay, I have 14 blank spaces. Where can I put the jumps? Well, I know that I'm going to have to start with a 1. I'm going to have to end with a 9. I'm now going to put just little circles here. I might put a jump here, 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 here. I could put, these are places where I might have a jump. There, all the spaces between successive spaces, beginning with after the first space and ending with before the last space. Now, if there were 14 spaces here in our combination, how many circles do I have, which are places I could put the jump? The answer is there are 13 possible places for the jumps. And what do I have to do? I have to pick 8 of them. I'll show you the one for this example here, this first example that we did. I picked there to jump. Then I have a single 2, a single 3, a single 4. Then I have 3 5s, so I'm going to put a jump here. Then I have 2 6s, so I put a jump here. I have 1 7, so I put a jump here. And then I have 2 8s and a 9, so I put a jump here. I have to pick 8 of those 13 spaces in order to put jumps. How many ways can I choose 8 of those spaces for the jumps? The answer is 13, choose 8. That combination number tells me exactly how many choices I have for where to put the jumps. Can we generalize this? Well, the answer, of course, is yes. So to generalize it, say we have an n-letter alphabet. I'll call it A1, A2 through AN, and say we have a combination of length K. I'll just put the spaces here. That could be any number of spaces. I'll just draw it as if it's 7, but it could be anywhere. This is length K. And I'm going to just choose to, because it doesn't make any difference, I'm going to choose to write the letters in my combination in numerical order, by which I mean I'll put all the A1s first, I'll put all the A2s next, I'll put all the A3s next, etc., all the way up to the A sub n's. So we know it's going to start with an A1, since the combination must contain every letter. So I'm going to remind you we want no missing letters. And of course, repetitions are allowed. We're going to end with A sub n. Now, how many jumps do I need to place? I'll just put possible places for jumps. I have to pick n minus 1 places for jumps. And by here, a jump, I mean a place where we switch from A1s to A2s, or A2 to A3, or A3 to A4. A jump is just a switch in the letter to the next letter. I need to pick n minus 1 places for the jumps, and how many possible places are there? The answer is anything between two of the spaces is a possible place for a jump. So there are k minus 1 possible places for the jumps. And in how many ways can I pick n minus 1 places from k minus 1 possible places for the jump? Our total number of ways to do this is exactly k minus 1, choose n minus 1. Notice it's k minus 1 on top, and we're choosing n minus 1 from that. And that should make sense. K, remember, is greater than or equal to n, and we're used to seeing the combination numbers with the bigger thing on top. And that certainly must be the case. It's okay if they're equal, but you can't have a smaller number on top and a larger number on the bottom. If that happens, that's just automatically 0. So the number of ways of doing this is k minus 1, choose n minus 1. In the book, this is formalized as standard problem number 5, which says find the number of combinations of a given length, k, from an alphabet of size n, where repetitions are allowed and there are no missing elements. The answer is what we just computed, k minus 1, choose n minus 1. Here's an example. How many combinations are there of length 5 from the set ABC, which have at least one of each letter? Well, we can write down immediately the answer, because this is exactly from standard problem number 5. Length 5, that means k is 5, 3-letter alphabet, so n is 3. The answer will be k minus 1, which is 4, choose n minus 1, which is 2. And what is 4 choose 2? Well, remember that's 4 times 3 over 1 times 2. Remember we have n times n minus 1 all the way to n minus k plus 1. In this case, it's just 4 times 3 over 1 times 2. And that, of course, is 6. You might remember that from Pascal's triangle, but you should get some familiarity in computing these combination numbers. So there are 6 ways to pick a combination from the set ABC, which have at least one of each letter. Let's write them down really quickly. There are only 6 of them. We could have AAA, BC. And think of this, I'm writing them as strings because it's easier to write them as strings, but you have to remember order doesn't matter. So it looks like a string, but we don't care about the order. It's really good to think about this as just a bag of like pool balls or any sort of ball where there are 3 types of ball or 3 types of labels on the balls, A, B, and C. And think of this particular combination as a bag with 3 A's, a B, and a C. You might have 2 A's and then maybe 2 B's and a C, or you could have 2 A's and 1 B and 2 C's. Of course, you might have 1 A and then you could have 2 B's and 2 C's, or you might have 1 A and just a single B and 3 C's. Or what might you have? You might have 1 A and 3 B's and 1 C. And try to think about it, you'll find these are actually all of the different combinations that include every letter at least once. Now, as a slight modification to that, how many combinations are there of length 8 from the alphabet ABC, which have at least 2 A's, 1 B, and 3 C's? So we need the combination to be at least 8. Think of that as a bag of 8 balls. and it must contain at least two A's, two balls labeled A, one labeled B, and three labeled C. Now that's only 6 that are spoken for. The rest, there are lots of ways to fill up the bag to make it have 8 balls. How many ways? Well, here's the trick. And when I say trick, you need to know what we mean by trick in mathematics. Trick is just some kind of thing that looks like it's pulled out of a hat that somehow lets us answer the question. Once you use this trick several times, we don't call it a trick anymore. It's called a technique. So this is really going to be an important technique for us for counting all sorts of different problems, especially when it comes to counting combinations. The trick is this. We have to have at least 2 A's, at least 1 B, and at least 3 C's. Think of taking your bag and put in 1 A and 2 C's. Now, why 1 A and 2 C's? Well, we need at least 2 A's. If I put 1 A in already, the remaining stuff I have to choose from will still need at least 1 more A. So I'm leaving the fact that I'm still going to require 1 more A. I'm ignoring the B's because here I just require at least 1 B. And since I require 3 C's, I'm going to put 2 in right away. And now just, what do I have left? If I've already put in 1 A and 2 C's, I only have to put in 5 more balls. And the only condition I have to meet with these 5 balls is that there's at least 1 more A, 1 more B, and 1 more C. Well, how many ways can I finish putting the balls in the bag? I need 5 balls. I need there to be at least 1 A, 1 B, and 1 C. Well, that's exactly the problem we answered above here. I need to just pick a combination of length 5 from the alphabet with at least 1 of each letter. So I can finish in 6 ways, since I need a combination of length 5 with at least 1 of each letter. So there are actually going to be exactly 6 ways to find a combination of length 8 with this condition of at least 2 A's, 1 B, and 3 C's, because the computation is exactly the same as the previous one after I put in what I have to put in, which is 1 A and 2 C's. Those are going to get in there anyway, so let's just say we do it. Finishing out the problem can be done in 6 ways.